there's an L1 regularizer on this, whereas 20 years ago it wouldn't have been there. So we have a lot of justification for regularization. We have a lot of reasons why we think it's very good, and we're using it everywhere. Then there's this interesting thing that there's the algorithm AdaBoost, which is verbatim doing coordinate descent on a convex optimization problem. But the standard formulation is not regularized in any way. And it has all these nice guarantees. So the question is, what's going on here? So what I was hoping to do in this talk is kind of go through AdaBoost and actually use AdaBoost to discuss kind of what's going on with regularization. So that was the hope. So just to make sure we're all on the same page. So regularized ERM looks like this. We have some kind of error penalty and we have some kind of regularization penalty. We're searching over some function class, and we want to penalize the algorithm from picking anything that's too complex. Typically, we'll have some representation for f, and so it'll be like a norm or something. But there's a lot of ways to write this. And like I was saying, a lot of the standard algorithms we care about look like this. For instance, whatever, LASSO, basically everything. So there are a lot of reasons why we do this. So one is just the optimization perspective. We add L2, and now it's a strongly convex problem. And so a very nice example of this is ADMM. So the way ADMM works is you add this, you do this augmented Lagrangian, you add this L2 term, and the L2 term just adds all this nice curvature. The problem before you do it in ADMM might not have good curvature. You add the L2, you feed it through LBFGS, it goes fast. So this is something people like a lot. Another thing is we are guaranteed to have minimizers. So our optimization problem has minimizers. This isn't in general true. And also it's numerically stable. The numbers just don't get that big, and it's just nice. Like for ridge regression, you can just interpret ridge regression as look at least squares. Sometimes you can't invert the matrix. How do you make a matrix easily invertible? Just add something to the diagonal. That's ridge regression. Okay. And that was just kind of numerical. Statistically, we have a lot of reasons we like it too. So I say generalization for free. What I mean for that is here's basically a one-line generalization bound for anything with a norm constraint. Or a norm, if we put a regularizer on it, we can convert that into a norm bound. Then we can just plug this into some Rademacher tricks. If it's a Lipschitz loss, in one line we have a generalization bound, no problem. So what I mean by a model exists is that once we're in the regularized framework, we're usually talking about some kind of recovery, and we have some nice model. And this will let us reason about how we can recover it. So for instance, for LASSO, we add this L1 term, and the L1 term can just swallow the noise. So the way it works for LASSO is we set the regularizer roughly proportional to the loss term, or sorry, the quantity of noise, and it just eats the noise. So those are nice properties. This is why we like. There's some of the reasons why we like regularization. Actually, let me just say that if you look at a lot of modern stuff with regularization from the stats literature, they have all these weird structures they're trying to recover from data. And often, it's just a really nice regularizer that'll just pull that thing out. So if you know of Pablo Perillo at MIT, he has all this crazy stuff he's doing where he figures out different regularizers and he adapts the regularizer to the thing he wants to recover. Okay, so that's regularization. Now let's look at what AdaBoost is doing. It has the same error term. It's just same as on the previous slide, except now instead of regularizer, we just write 0. So this is literally what we're optimizing in AdaBoost S written by Rob and Yoav, almost 20 years ago. You're doing coordinate descent on this thing. So just to be clear, when people talk about AdaBoost in literature, often they're talking about something else. So sometimes people add an L1, they add all sorts of things. In this talk, just the original. And so how do we do with all these properties we really liked, right? These are good properties, right? They all sound pretty reasonable. So first of all, strong convexity is out of the window, and it's super out of the window. I can just take two weak learners and make them linearly dependent or something. You look at the Hessian, the smallest eigenvalue is 0. So no strong convexity. Don't have minimizers. Here's the case with no minimizer. One example, one weak learner. So your AdaBoost, you're just minimizing e to the x. Where's the minimum on e to the x? On the other hand, e to the x is easy to minimize. So this shouldn't actually be a problem. Numerical stability, so if you look at the original algorithm, the step size, it suggests, is 1/2 log 1 plus this gamma t, 1 minus gamma t thing. So, gamma t could be 1. So it's telling you to take an infinite step. So it's not, strictly speaking, numerically stable. Nothing prevents the algorithm from getting too big also. We don't have generalization for free because we have no norm bounds. So we can't just apply the Lipschitz-Rademacher thing I mentioned earlier. A model does not necessarily exist. If you use the logistic loss, then if the minimizer doesn't exist, then you're not recovering any, if you're doing logistic loss minimization, it's like, it's like some kind of a posteriori thing. But actually, you might not have a model. So, and then I was going to cross out this last one just to be really rude, but part of the point of this talk is going to be that we still do actually have nice recovery properties. They're just not kind of the usual ones. Okay, so far though, it looks pretty bad, right? Like, why would anyone ever use this thing? Like, I don't know. I mean, I think these were pretty kind of easy properties. People like these things, but they all failed. And so the reason we like the algorithm are two different guarantees. And so I picked what I personally feel are the main reasons the algorithm works well. So the first one is what I call the favorable case guarantee. If there is a large margin solution, the algorithm will find it and it's statistically stable. So just to be clear, this is not the standard weak learning guarantee that people kick around that just says the training error goes to 0. The training error goes to 0, that isn't as strong as this. Because training error goes to 0, if you want to, let's say, apply the VC theorem to see how, see what your generalization error looks like, the VC dimension of this class is going to scale with the number of iterations. But this thing doesn't care about the number of iterations. This is a slightly different guarantee, and I will go over this in detail. But I think this is a very nice guarantee. If there's a large margin solution, it is found by the algorithm, and it has good generalization performance. The other one is the consistency guarantees. The consistency guarantee says if the Bayes predictor, so whatever, sign of PR, probability that y equals 1 given x is greater than equal to 1/2, if this thing is Borel measurable, which is, it's like not that big, not that much to ask for, and the weak learning class is big enough. So if we have some nice decision tree class, then the algorithm finds it. That's a pretty good guarantee, and this is the guarantee at the heart of let's say, the Bartlett-Traskin consistency proof, and that's from only 6 years ago, almost over a decade beyond the creation of the algorithm. So I think these are the two. For me, these are the reasons why the algorithm. If somebody puts a gun to my head and says, "Why does the algorithm work?" Well, number two, if you know something about your problem, you can pick the hypothesis class to be well adapted, and you get good margins. If you don't know anything about the problem, you can just try to make it fit everything. So that's the first one. The first one's basically a non-parametric guarantee. So what I'd like to talk about in this talk is I'd like to sketch actually how to prove both of these in a way that looks like I'm being regularized. So I'm going to prove them by basically showing that the algorithm is doing something that has great it almost looks like I have a regularizer. So and I came to this because as a grad student, I was just trying to prove things about boosting just because I like math problems, because they looked hard. But it became really creepy just running into all these all these implicit regularizers everywhere. It just was very strange. So I started thinking about it more and more. The second thing is, it's also nice to look at these two guarantees, not those 6 we wrote previously, but these two guarantees, and see how the regularized algorithms work on these two guarantees. Because these sound like good guarantees as well. Maybe the others weren't that important for some problems. Okay. So this is the outline of what I'll talk about. It's 7 items, but actually they're all about 2 slides, so it shouldn't be a big deal. And kind of in the way I think about this problem, it became very natural to think about 2 cases, a non-separable case and a separable case. Let me just tell you what I actually mean by non-separable. I don't mean the usual thing where we have a finite training set and it's a linearly separable problem in the training set. I actually mean over the distribution. So if you look at the population problem, we can get 0 error there. So I'm talking about the expected risk here. So when I say non-separable, I mean expected risk. When I say separable, I mean expected risk. And this has these very strange phenomena, like it can be separable, but the margin is now a random variable. And so we can't actually guarantee that the margin is a nice positive constant. So this view incurs that kind of complication. But OK. So the first thing I'm going to do is just kind of explain some notation and stuff. And I also wanted to give a history of the algorithm. And the reason I wanted to give the history of the algorithm because I think the fact that the algorithm is not regularized is very tied to its history. So the first thing was Kearns and Valiant. They had this conjecture that weak learning implies strong learning. And this is an interesting conjecture both because Valiant, of course, is a theorist, and the packed learning statement is a very kind of theory-like looking statement, and also this was, Mike Kearns has a cryptography background, so this was like a very cryptographic question for them. And then so Rob Shapiri proved that you can actually do this, and he had this ternary tree construction that if you take Avram's class, you'll see it, and then actually. It looks like the same year, but there was enough time here for I just want to make the chronology clear because both these papers look like they were published the same year, but actually Yoav had time to talk to Rob, and if you look at Yoav's paper from 1990, which is a little hard to find because it's not on his website, for instance, he has a 1995 thing. The 1990 paper is really, really nice, and it shows that you can just use a single majority, which is pretty awesome. And then they have AdaBoost, which is what we're talking about now, and they have this this funny paper title where they like. I mean, this is a good algorithm. It's like it's like the 50th word of the title, so this is kind of funny. Okay, so now this is where things get really exciting. So, well, sorry, they were exciting the whole time, but so Rob Shapiri and actually, yeah, all the authors. It's Yoav Freund, Peter Bartlett, and I forgot their first name, but Lee. So this paper is the one that I was for that second guarantee I talked about. It's a margin bound. It has generalization without any stopping conditions. The margin gives you generalization. So that was from 97. And then it took this long to point out that the algorithm looks like loss minimization. So I attribute it to Bryman because I think people say that's who was the first, but the publication record's actually a little complicated who published first. Like there's a Bartlett paper from 1999 that, whatever. But there's also a 1998 paper by people that no one really cites. So, but apparently it was from Bryman. But this is interesting, right? So now if I were to give you the boosting problem, if I were to write down for you formally the problem, you would probably just say plug it into regularized ERM. It wouldn't take you 12 years to go from or whatever, 8 years to go from the problem to ERM. I think that's important. And so the margin bound just says that large margin solutions are stable, but no one's actually proved it that the algorithm finds them. So that took a while too. And so it was here that this first guarantee I talked about, so this is Bartlett and Traskin, they show the algorithm's consistent, and this is that thing I talked about where it converges to basically whatever you want. Okay, so let me just give some notation because I think it makes the problem easier to think about it this way. So we'll have a class of functions which are the weak learners. So we'll be combining these to, this is how boosting models things, just takes all these little functions, adds them together. And I think a nice way to write about it is to collect all of these functions into a big matrix. You can call it a matrix if you want. I mean, technically it's a linear operator because all the dimensions are infinite, but it just looks like a matrix. So at this point, we can almost view this as just like a standard linear learning problem. You can just forget everything is infinite. And so yeah, the algorithm, it learns these thresholds, and there are two ways to choose this class H. So the first is we want things to have nice representations. We want to bias it towards having these nice large margin solutions. If you don't know anything about your problem, you can't do this, but we'd like for this to happen. The other thing is that we want to be able to solve these correlation problems. So the way I wrote about it here is if I look at, so my view on this is based, so this is another vector. This is some finite sample, and this is a vector of length m, which is some specific hypothesis h prime applied to each example and then multiplied by the y. So it's this nice vector, and I'm correlating it with this thing. So these correlations, so I want this to be basically the biggest one. And I wrote suit because there might be infinitely many of these guys. So I want to be able to solve these correlation problems for any p. This is how you pick this class. And if this looks like a tall order, this is a tall order. Most implementations, they don't actually solve this. And so most implementations of boosting don't carry any of the guarantees anyone talks about, because they don't do this correctly. And they can't, because it's NP hard. So, OK. All right, so now let's write down the minimization problem. I'm going to introduce one more piece of bureaucracy. If I just negate things, that's to me this matrix A. So forgetting about the minus sign for now, if that term, if we're correct, then we're going to agree on the sign with y. So that's basically the margin without y. And I'm just flipping it. So if I'm correct, it's going to be, if I'm very correct, large mark, it's going to be a big negative value. If I'm very wrong, it's going to be a big. So the reason I use this notation is now I can just plug this into a loss, and it looks very familiar. So let me actually just expand it all the way out. So the reason I did this notation is because now this looks like a really convenient linear learning problem. It's just as comfortable as we can get. We can forget about all these formalisms of infinite function class and all this nonsense. It's just a linear learning problem. But going back, so yes, this is just an unregularized ERM. And this is the representation of this with all these functions. And the W is all the weights. So it's just a linear learning problem. And I was careful to handle infinities everywhere, but for the purpose of the talk, you just forget the infinite things are problems. When you actually stand on proof things, you have to worry about it, but not now. OK. So the way that the algorithm works, AdaBoost is verbatim just coordinate descent on this thing. That's all it does. And just two things. One is we are going to have an early stopping rule. So you might say, well, early stopping is kind of like regularization, so you've already put regularization in the problem. That's slightly true, but the first regularization guarantee I'll prove is before the stopping condition is hit. The second thing is you kind of need this. The second, and I'll discuss how you need it. The other thing is that how you choose your steps really matters. But the original algorithm is just a coordinate descent thing. OK, so now let's do the only real proof we're going to do this time, because I think this proof is pretty interesting. OK, so what we're going to show is we're going to try to show this guarantee that we can basically fit anything over, can basically fit anything. And so I'm just going to specialize a little bit. I'm going to require my loss function to be Lipschitz. So this holds for logistic loss. And this proof, I am about 90% of the way to getting it for the exponential loss. But yeah, we'll have to have a Lipschitz loss. I'll discuss that gap in a minute. But OK, so what we want to prove is we're going to show that. So I've dropped the hat. So this is just the expected risk. So the expected risk of this thing we have after t iterations of coordinate descent, it's going to be as good as the best possible thing within some radius plus a bunch of deviation terms. So the first deviation term is basically the deviations of this guy up here. So the way the proof works is I just prove an optimization guarantee on WT, and then I have to do a bunch of conversions. And so, for instance, this thing is just what I'm paying for that guy. There's one trick I'm leaving out, but we'll see it in a second. And so these two terms, they come from the optimization guarantee. The problem with the optimization guarantee is that this constant is between 0 and 1, and this is an analytic artifact. So that should probably be like 1/4. But I'll explain that artifact in a minute, too. But so this is the kind of thing we want to prove.
What's lambda?
Oh, I'm so sorry. I switched notations. Although that should be W.
Okay.
Yeah, that should be. So it's infima over W. So we're comparing ours to the best one within this radius. So one interesting thing I can say right away is that a similar thing was proved by Rob Shapiro and his colleagues, and this is how they got a very nice consistency guarantee for regular AdaBoost. But for the exponential loss, they had to take a number of shortcuts. For instance, they aren't able to prove this exact statement. They have to clip the function, because with the exponential loss, it just gets too large at certain points. The other interesting thing here is that here we're competing with the best guy that has a length of root t. What's going to be the really kind of surprising thing is that the WT, we're going to prove the main thing that lets this proof go through the main lemma is that our WT also satisfies this condition. Our thing is also lives within a small norm ball. And that's the implicit regularization that the whole talk is based on. And for instance, they were not able to prove such a thing for the exponential loss. And I'm not sure what the exact thing is for the exponential loss. But yeah, so there's this ball that everything's going to live inside. And so you can see if you look at the bound that it tells us what our early stopping should be. Because if we make it bigger than m, then this thing doesn't go to 0. And so the proof I mentioned by Rob Shapiri and a bunch of his colleagues, it gets basically a rate of m to the minus 1/9. But the comparator function is much weaker. And you might stare at this and say, oh, isn't this just a maximum likelihood statement? If we use logistic loss, can we just use consistent maximum likelihood? The answer is no, because we don't have either a minimum or we're not in finite dimensions. And I'll go over some competing statements for this, but it almost looks like it should be down to square root. OK, so oh, yeah, and so the way to get the Bayes predictor is to make the function class large, and I'll explain that later. OK, so let's go through this proof. So what we're really going to work with, so this is going to be our key lemma. We're going to prove that these things are small, at every iteration that they're small. And the O is not going to hide anything sample dependent. It's just going to be distribution and function class specific things. So the interesting thing about this is the algorithm isn't constrained in any way. The steps, by just the way the algorithm is written down, they could be unbounded. There's no projected gradient or any of this stuff. So something is causing that wave vector to be small. And if the lemma looks kind of obvious to you, I warn you that this lemma is actually false in general. So I said I'm in a non-separable case. You can interpret that as being there's noise. And the noise will cause the vectors to be small. So this lemma is definitely false in the general case. The algorithm will just take really big steps. It'll look more like, it'll grow more like theta of t. Like I said, I'm almost there for the exponential loss. And so what's interesting is that the previous statement, the previous theorem that I showed you, after I prove this, I can just drop this analysis into this analysis by Tong Zhang and Bin Yu, which worked for an algorithm that explicitly restricts the step size. They had a regularized algorithm that explicitly restricts step size. I took logistic loss. I proved that it implicitly maintains a certain growth rate on the step sizes, and it was exactly their step size condition. So it was interesting that they had to assume a certain structure or enforce it through an algorithm, and it turned out that structure was already there. So that's kind of the idea behind everything in this talk, which is that we end up getting these regularity conditions that people often impose algorithmically or by assumptions. They're actually already there in the algorithm, or sorry, in the data. OK, so here's the proof. And so kind of I think whenever someone's faced with having to prove something about a convex problem, kind of the first thing you do is just write down the dual. If you don't know what to do, you just write down the dual. And just kind of stare at it. So because we have to prove that some wave vectors are norm bounded. Why would they be norm bounded? There's no norm bound in the objective function, right? It doesn't even seem true. So OK, here's the primal. And so here's a picture of the dual. So the primal is just this e to the x thing, and the dual is explicitly a max entropy problem. I mean, it's just like if you look at exponential families, for instance, like it's the same exact functional form. This is exactly a max entropy problem. But the question, though, is max entropy always has a constraint. And so the question is, what's the constraint in the dual? Does anyone know, by the way? It's pretty weird. OK, so I'll
constraints are normally that the data moments agree with the moments.
Yeah, so it's going to be some linear constraint. It's definitely a linear constraint. Yeah, that's what this green, oh my God, I don't know how to operate my machine. OK, here we go. So this green region, this is the constraint set. Oh, and one reason why going to the dual is nice, because look, the primal's nasty, right? No minimizers, what's going on? The dual, though, is, has maximizers. It's like curved. It looks easy, right? Everything is nice. And then it has this weird linear constraint. OK. All right, so here's the English version of what the dual is. So it's an entropy over a family of distributions that reweight all the examples. So that just means the reweightings of the distribution that we drew from. I used whatever. I used this notation for a distribution. And then the constraint is they decorrelate. So that correlation expression we had, it was like sum over the examples, yi, hxi, pi, you get 0 for everything. So that's what this thing means. It means the domain of this maximization is all the measures so that all those correlations are 0. So this is really, really interesting because what is the weak learning assumption? Weak learning assumption is for any distribution, I have some h that gives me an edge. This is saying if this thing is not a trivial set, then that's saying I have a distribution that whatever you feed me, it's not correlated. So this is kind of the anti-weak learning assumption. That's already really interesting. The dual has the weak learning assumption baked into it. And so again, so if the weak learning assumption holds, this thing isn't just being 0. The feasible set of the dual problem is 0. And the entropy functional, it's just 0 at 0. So everything makes sense. We have our feasible set 0, the objective value 0, and the optimization problem the training error by Rob's result goes down to 0. So everything makes sense. Yes, this is our space. It's that linear space. Oh, so it's a linear space, which means there can be negative distributions. But then the form of the entropy will restrict it to be non-negative. So here's the math version of it. So if you're familiar with Fenchel conjugacy, the loss just gets conjugated. And so the exponential loss, it's one kind of entropy, and the logistic loss gives another entropy. So it's really just that. It's really that clean. And those constraints, that's one way to write the first one. And this looks kind of, I guess, gross. I never know if I should include gross. Okay, it's gross. Sorry. Okay, so now we have to do something with it. So now we have to do something with it. So here's the key observation. So we're non-separable, so that thing's going to be non-zero. It's non-zero, that means P isn't just the 0. It's not just a trivial distribution. It's a distribution that puts mass in some places. And this is max entropy, so it's trying to make it as big as possible. It's trying to find this very nice flat distribution. And notice what we can do with the constraint. We can just split the constraint into negative margins and positive margins. The reason this says positive and this is less than 0 is because I had that negative sign in there. So I've just taken this equals 0. I just split the integral into 2 parts. Okay? So what this is saying is that this dual optimum, it says, give me a weight vector and promise and pretend to me that it's a good weight vector, that it does well on this problem. Well, I'll say, no, you're lying. If you give me this vector where it's positive on a lot of stuff, I can say it's negative on a lot of stuff. So just by flipping that constraint, I get this equal sign that just says, if you're positive on a lot of things, you're negative on a lot of things. So that means every solution is terrible. In other words, if you're doing the algorithm and you're searching for a step, every direction will eventually have to go making a lot of mistakes. And the way convex losses work, you start making mistakes. If you take a step too big, it'll penalize you more than for the correct ones. So for me, this is kind of magical. It's basically the dual constraint encodes this anti-weak learning thing, and then we just split the sum into 2 terms, right? I've done nothing here. And it's really that simple. So in the actual bounds you prove, properties of the dual optimum are part of the bound, just how big that thing is. And it's almost like the dual is trying to make the bound better, because it's maximize the entropy of this thing. It's just, I don't know, it's kind of magic. So I left out one thing, which is that this was on the distribution. P was a distribution object. I have to manage sample effects. And actually, this is really nasty. So here's a weird example. Suppose that the model is correct in the sense that I have the base, just pick an h, okay? Pick an h that's always right. Or sorry, pick an h and we're going to make it always right. We're going to pick an h and make a distribution. So pick an h, but now add label noise, 10%. And assume the probability distribution is continuous. Continuous, that means with probability 1, I'm never going to sample the same point twice. So even if we have 10% label noise on a distribution, every sample will look separable. And so, especially if you pick some really big class that can fit everything, you're always going to be looking like everything has no noise. But the way around this is that it only looks like you have no noise if you work with small functions, or with big functions, if you allow it to fit everything. So we just clip the thing. So that's why I said the early stopping is basically necessary. Without early stopping, this looks like one nearest neighbor, which doesn't get the optimal loss. So that's my explanation of what happened here. So the population dual optimum, it ends up being a certificate. So people talk about this dual certificate stuff. This is just another dual certificate. And it prevents any descent steps from being too big. So this is why that root T comes in. The dual optimum just says, no, don't go farther. OK, so here's just a bunch of results. I just wanted to kind of put this in context of the literature. So the m to the minus c is what we just proved. The m to the minus 1/9 is this, well, the consistency result is in the book, but the open problem that they had to solve that Rob had to solve with his students was before that. But anyway, the bottom line is that it looks like you can get all the way down to -0.5, but there are a lot of caveats. So it's really unclear what the boundary is here.
You said you think your C is actually 1/2?
No, oh my God, no. No, I personally have no idea there. Rob thinks it should be -0.5, the exponential laws. And he has this other algorithm. So this thing is really magical, and this is like exercise 12.4 in his book. I only know about it because he told me like a couple years ago. But so the algorithm is, after every step, you shrink back. That's really the algorithm. There's another kind of step search. You take a coordinate step, and then you shrink a little bit. You take a coordinate step, you shrink a little bit. Right? It almost looks like LASSO. It's doing the shrinkage operator. So this thing gets basically the -0.5. There's some caveats there, but so I think this is why Rob thinks it's -0.5. But definitely, so the SRM booster, this is this crazy thing, right? It does like this infinite family of classes, and it's it's not an implementable algorithm. This is some like crazy penalized thing, right? The L here is Lugosi, so this is Gilles Blanchard, Gober Lugosi, and Viatis. So it's not an implementable algorithm, but 1/2 seems good. Okay, so let me tell you briefly what has been meant by big enough. Or do we have any other questions? Or I got worried that I had too little material and I went too slow, and so we got confused about the timing. But okay. Okay, so I just want to tell you really quick what classes are big enough, because in a lot of papers it's a little bit murky how big you actually need to make these classes, and a lot of times they have strange assumptions like, oh, like in one of these papers it says, the weak learning class should fit all measurable sets. It's just such a big class of functions. So I want us to prove that you can just use just tiny decision trees and you're done. Okay. And just the motivation for this is that, I was saying that margins get good rates, but we don't always know what the right class is to get good margins. So we want a good 0-1 loss. That's our backup. But the problem with wanting good 0-1 loss, well, if there's 0.01% noise, then it's NP hard to do better than random guessing, or better than 49% or whatever. So wait, does that need UGC? Oh, that's right. That's from the PCP theorem. Okay, that's a reduction of PCP. Okay, thanks. So, what you need to do is you need to make your class really big. And one way to do it is to make it dense in bounded measurable functions. What you can't do is just put the Bayes predictor in the class. That's not good enough, and there's this example by Longster video that defeats that. And stumps aren't good enough. They just can't fit very much. But we can use axis-aligned decision trees of depth D. So we're just going to prove this in like 2 seconds, so that we never have to worry about it again. Okay, step 1, can your class make corners? So what I meant by those arrows is we can just fit these, so we can fit these rectangles that You pick a point, and we go infinitely in all these other directions. We just get a corner. Okay? We add together a bunch of these, and we get a square. We need actually 2 to the d of them, if I'm not missing, maybe 2 to the d minus 1 or something. But you get a square. Then you can just fit anything. So what I meant by this is the Bayes decision boundary, and we're just kind of fitting around it. Here I drew it as a continuous curve. You can use some analysis tricks to drop the continuity assumption. So you can literally fit any Brill measurable function with this. And just, you can actually also, this is a pretty useful proof technique. You can prove neural nets can fit everything this way too, 3-layer neural nets. It doesn't get the 2-layer, but 3-layer neural nets can fit everything from this. It's just, you can use this to prove everything. So, okay, every like non-parametric class. So, but there's a problem. So here's the problem. In this proof, I needed us to be exactly solving that correlation problem. So I needed you to be finding the best D depth decision tree. And how many of those decision trees are there? Well, you're going to have to look over n to the d. So we've explicitly baked in a cursive dimension. So what people do in practice, they run cart, but cart's not solving this. And another way you can see that we've messed up somewhere is, for instance, we could learn parities with this, right? Just make parity, just take the hypercube, just label things with parity. We could just knock out each corner with one of these boxes. How are we going to find those guys, right? There are lower bounds for juntas and all this stuff, and so we know that we're basically paying this something close to this end of the d. So I think this is something that I think there's a lot of room for improvement here. I mentioned kitchen sinks, which are these nice. This is a really nice paper by Ben Recht and Ali Rahimi. And so the kitchen sink paper is actually kind of stated as a boosting paper, but if you look at it, you'll notice they have a constraint everywhere, so they're actually doing regularized ERM. But yeah, okay. So let me tell you a little bit about the separable case. And so the story, as I've told it to you so far, looks like this. So I told you that for the exponential, we can do this 1 minus 1, 9, and here I told you we just get this constant. Okay? This is a story as I told you so far. And then I also mentioned that there's this little bit of a detail that the margins can actually be so small they're not useful. So technically what's going on is if you look at the margin bounds, they have a 1 over gamma squared, 1 over m term. So if your margin is less than 1 over root m, that bound isn't going to go to 0. So that's the kind of thing you're dealing with there. There's also actually a split for the non-separable case where you have a model or don't, but I won't go over that. But what's really nice though is when you do have good margins, you get a very good rate. You know, this is better than anything we wrote in that other table. And in the tiny margins case for logistic loss, you can prove an m to the minus 1/3, but I won't I won't tell you how. But it is a very different proof from the earlier one we gave. But you can do that. So the interesting thing here though is we have no stopping condition. We don't need to artificially constrain the capacity. The margins will do it for us. Okay, so let me just go over some previous results here. So there is a nice algorithm by Gunnar and Manfred Warmuth, and also Scheisele Schwartz and Yoram Singer, that it just solves an LP. Okay, you look at this thing, what is margins? Whatever, just some stupid LP. Just plug it into whatever you want. So they have a coordinate descent solution, and it takes this long. So it gets, if gamma is the minimax solution or whatever you want to call it, the game theory, whatever, just whatever you want to call it, they take that long. Now, what's interesting is that you can prove the following for just vanilla AdaBoost. You can prove that it takes fewer steps than that to get a fourth of the best margin. And I'll tell you why that's true in a minute. But I already find this pretty nice because that means you're doing almost as well as an explicit algorithm, right? I mean, this algorithm up here was just designed to solve that problem explicitly, and this one gets pretty close. Also, there's a barrier here that this algorithm verbatim actually has a gamma over 2 negative case, so it can't do better than gamma over 2. That's kind of interesting. And if you do something called shrinkage, where you kind of pull back, you apply a little bit of regularization inside the step search, you can actually get all the way to recovering the explicit algorithm's result. So let me just tell you really quick why this is true. So if I draw the function, so if I just assume we have two weak learners, and I just draw the objective function we're trying to minimize. So this is the weight on the first weak learner, the weight on the second weak learner. So I've got this set of level curves. So these are level curves. You know, each one of these curves denotes a constant value for the objective function. So according to descent, what it's going to do is just going to follow a valley. And to get a better sense of what it's doing, I'll draw the L1 constrained solution for all sorts of different values of the constraint. So this line is what you would do if you just fixed an L1 constraint and just solved the problem. It's kind of the way to look at the max margin solution at very different levels of regularization. So the algorithm, what it does, is just follows the valley. It can't go too high because it just hits. And actually, if you look, I generated these pictures programmatically. You can see this is a, because it's a convex optimization problem, it's going to do the line search until it hits the first order condition. And the first order condition equivalently tells it that it's going to be perpendicular to the level curve. So it's kind of very intuitive that it does this. If you make it smaller, it approximates it more finely. So so this is another case where the data itself constrained the behavior of the algorithm. And I found this interesting because usually when people talk about margins, there's a regularizer floating around. SVM is a margin thing, and it has an L2 regularizer floating around. And both of the explicit margin solution boosters that we talked about earlier, the Scheislev, Schwartz, and Rech and Varmuth, they both had explicit regularization. But so this algorithm doesn't need any regularization, gets the same rates, and it just follows the value that the data plugged into it. Okay. So let me just kind of end on a light sort of funny thing, which is, this is just a bunch of theory, but you have to worry that it's loose and it doesn't mean anything. So the question is, why don't you just run the thing? Because you actually see this stuff. And you can guess the answer is yes, otherwise I wouldn't show you. But so this is the separable case. And so what we want to see is that I was not lying about this statement being false in general. And I'm going to draw the primal iterates and the dual iterates. The dual iterates are just you pass things through a gradient. And the dual optimum I claimed earlier was 0, so these guys should all converge to 0. And here, this should look, well, obviously I made the slide, so I know what it's going to look like, but this should be violated. It should grow. It should just grow dramatically. And this is a log. This is, each of these grows by factor of 10. It's log whatever, log plot. So it grows just like that. So you can see these guys are growing at a rate of t, and they just dramatically quickly they grow very. And here everything collapses down to 0. And then the non-separable case. Oh wait, did everyone? Yeah. So I don't know. I explained it before we saw it, so it wasn't as dramatic. Okay, this one I just won't explain. I'll just make pictures happen. And then I'm cluing you in here that we have a non-zero dual optimum. This shouldn't go to 0. Okay. So if I run it, it looks like this. So the first thing you notice is that it's not blowing up as fast. And what's strange is that it actually goes at a rate of log, which is something that happens when you try to prove lower bounds for boosting. The other thing that you notice that's weird is that there's these guys that actually are just constant. They just stop. And there is a concrete explanation for that. You can prove that that object exists, and you can write linear programs that just find it. And it's something called the hard core, which is a cryptographic concept. And yeah, that thing exists, and it's unique, and it has all these nice properties, and it relates all sorts of ways to the optimization problem. I'm not going to tell you about it, but this is a fascinating thing that happened to me. So when I was preparing my thesis, I was looking over all sorts of notes because I wanted to make sure I can talk well. And I went back to the first time I ever learned boosting, which was from Arvim's class that I took as an undergrad. And this is one of the first paragraphs in the first lecture. And randomly, this phrase hardcore is in there. So I just wanted you to know that yes, there's a hard core, and I'm not making it up. It's a real thing. And but in crypto, this is it's a very familiar concept. I was explaining this phenomenon to Mike Kearns, and he interrupted me. He said, "Oh, you're talking about the hard core." I was like, "Oh, yeah, I am. Okay, you know more about this than I do." Okay, so that's what's going on. This thing has a name. It's real. It's amazing. It's called the hard core. Okay. I'm actually wondering if like you primed me mentally, that I like knew about this thing, because yeah, okay, it's really, really weird. Okay. Okay, so let's summarize. Okay, so the unregularized ERM, we proved that we didn't impose things algorithmically or in the objective function, but the data puts really strong constraints on what it does, and these constraints actually look kind of similar to the regularizers we often apply to things. But what was interesting was to recover one type of guarantee, the margin constraints, we used one set of regularized problems, and to recover the nice worst case bounds, we used a different family of regularized problems. So we used two different ones, and in particular, for all those regularized problems I talked about, like the crazy SRM booster, no one's proved that it, it has nice margin properties. Actually, I can tell you that it does appear that there is an algorithm that just applies a little bit of regularization in the step search, and it gets all the optimal properties. So it looks like that might be basically the optimal algorithm, which makes sense because in practice that's what people do as well. They use like a line search that's cutting. And as far as those properties that we said were failing, there's this quote by Vapnik that says, "Never use a more complicated subproblem." So one thing people do with LASSO is they say, "Oh, in order to get a good risk guarantee, I need parameter recovery." They prove their risk guarantee by getting a parameter recovery. But in order to prove parameter recovery, you have to assume identifiability. You have to have RIP, blah, a million things. So if you don't care about, there are a lot of natural problems where parameter recovery is what we want. I'm not saying it isn't, but sometimes it's not what you want. And okay. And I was going to, regularization, the real reason we do it is to control the capacity of our function class and to have some nice friendly bias. We love LASSO because we know under those conditions, we can construct the matrix, we can make the LASSO find the support. It just solves the problem. And here we also identified, in this margin case, that's what we care about. The algorithm works. And then I just wanted to thank all these people. In particular, I've been getting a lot of help recently from Alec Agarwal at MSR, and John is my host at MSR. And Rob is actually also at MSR. So basically, if I say anything wrong about boosting or regularization, you got to wonder about me because I've got all these people telling me how it works. So okay, that's the end. Thanks.